Okay, so welcome to the Graduate Student Symposium. Where the first talk, I guess, traditionally is given by a professor, so we're going to hear from Professor Mao from physics today, and then all the next weeks we're going to hear from grad students in various STEM fields to hear about their research too. So just a little introduction. Professor Mao started at Michigan in 2012, and she got her PhD at U of Illinois at Urbana-Champaign in 2008 in condensed matter theory, and she's still doing condensed matter theory here. So we're going to have 15 minutes for questions at the end, but please do shout out your questions throughout the talk. Because this is supposed to be a little bit more of a casual, fun sort of discussion. Or since this meeting's recorded, if you'd be more comfortable, I can keep an eye on the chat if you'd rather type your questions there, and I will interrupt and repeat the question if you'd prefer that instead. So, okay, Professor Mao, I think you're a co-host already, so it should work for you to share the screen and everything.
Okay, yeah, so can you hear me?
Yes, we can hear you.
Yeah, thank you very much. So I have to say that my computer is restarting and I'm joining from my iPad. So I think it will take 1 more minute for it to open the file. Sorry about that. It just started restarting right before this. So yeah, I'd like to just start by saying that it's my great pleasure to present at the Physics Graduate Student Symposium today. And it's my great pleasure to meet all of you again. So please give me 1 minute to start this on my computer so I can so I can share my screen from my computer. Okay. Yeah, so just 1 second.
Can I ask who your advisor was at UIUC?
Advisor? Yeah, I worked with Paul Goldbart.
Oh, okay.
Yeah, I don't know if anybody knows. So he is right now at Texas Austin. Yeah.
Yeah, I'm wondering because I did my undergrad there, so maybe I would have. I don't.
Oh, I see. Yeah, he left quite several years ago. So I don't know if you met him.
No, I didn't have the opportunity, but yeah,
Mm-hmm.
that's cool.
Okay, so yeah, I think my computer is ready. I'm going to sign off on my iPad and then join from my computer. Just 1 second, okay? Okay, hello everyone. Can you all see me now? Okay, yeah. Sorry about the technical problem. So yeah, let me share my screen now. Okay, so I go to slideshow. And use the laser pointer. Okay, so hello everyone. So just saying again, it is my great pleasure to see all of you. And hopefully we will see each other more in the fall semester when we all go back. So today I'm going to talk about our recent work on frustrated self-assembly of non-Euclidean crystals of nanoparticles. This is a very new direction we're trying to start in my group. And so far we just have one preprint here, but there are a number of ongoing projects and we are very excited about this new direction. So I think perhaps more of you know me about my work on topological mechanics. So I'm not talking about the topological mechanics today. And so do I, oh, okay, it's admitted. Yeah, so the one interesting effect from the pandemic, I guess, is that now a lot of talks are online and they are all recorded. So if you're interested in topological mechanics, you can go to my webpage and click talks, and there are a number of recorded talks on topological mechanics. So just in case anybody is interested in that. So today I'm talking about this new direction on using non-Euclidean crystals to understand the self-assembly. And here to give you an intuitive picture, this is a picture of a non-Euclidean crystal, in fact, a part of a non-Euclidean crystal. And it is a crystal in the sense that if you sit at each unit cell and look around, it is exactly the same environment that you see. It looks distorted in this picture because it's a projection from 4D to 3D, but the actual crystal is perfectly ordered. So these are mathematical objects that has been known for a long time. They are often called a regular polytope or space honeycomb, and they represent crystalline structures that live in non-Euclidean space or curved space. So what we are trying to do here is to explore whether we can learn something about interesting new physics in terms of self-assembly using these non-Euclidean crystals. So that's sort of the big idea. So to start, I'd like to motivate this question by inviting all of you to think together about what do we mean by complexity of structures of materials. So what do we mean when we say the structure of this material is more complicated than another material, right? So often what we refer to is information entropy, right? So when you think about complexity, there are clearly two different limits. In one limit, you can have materials that are perfectly ordered, like this crystal. And in another extreme, you can have materials that are completely disordered. Like I'm just showing you one random example where the position and the orientation of the building blocks are just random. So in terms of information entropy, which is basically how much space you need to take on your hard disk to store the structure of this material, you can say that the disordered limit is much more, has a lot more information entropy. So in this sense, it's a lot more complicated than the ordered limit, because here you need the detailed information of all of the positions and orientation of the building blocks. Okay, so but then on another hand, if you try to describe the physical properties of these materials, you will see that the disordered limit is actually not that much more complicated than the ordered limit. For most of the physical phenomena you want to describe, it is possible to write down a low energy theory that did not need the detailed information of the structure here. So then in this sense, this disordered limit is not that much more complicated than the ordered limit, right? But then on another hand, we know that in between order and disorder, there are structures that are truly complicated. And here I'm listing some pictures, and these pictures really speak for themselves. So they sit at the middle between order and disorder, and they are truly complicated, and it's not possible to write an effective theory to describe their property easily, right? So to capture this feature, there is this new concept called effective complexity that, to my knowledge, was first proposed by Nobel laureate Mary Gell-Mann. And the concept is really capturing the non-random information in some system. And he argued that in the middle between order and disorder, there is this so-called Goldilocks zone, where you peak at effective complexity, and that gave the system perfect efficiency, robustness, adaptability, and multifunctionality. And he also argued that our nature is running at this Goldilocks zone. And we know that for these examples, the effective complexity peaks as a result of evolution. So the many, many years of evolution help us reach this sweet spot between order and disorder, where you get very nice properties. And then on another hand, you can, for us as physicists, we can think about the question, can we engineer the assembly of these complex and yet ordered structures without using any biology? Can we use, for example, inorganic nanoparticles and reach complexity like this? And another way to think about this question is, are these structures completely hard-coded from biology? Or you only need a minimal set of genetic information, and physics and biology and physics and chemistry and geometry can do the job without biology to give you complex order. Right? So these are interesting sort of philosophical questions for us to think about. So to discuss that, I would like to show you an interesting picture. So I don't know if any of you remember this picture. I don't know any of you have seen this image before. So yeah, I'm going to show you the interesting story of it. So this was a picture that was taken back in 1996 when a group of NASA scientists tried to use TEM to study a meteorite that was believed to come from Mars. And in the meteorite, they find a structure like this, which if you look at the shape, this is a fake colored TEM image. If you look at the shape, they believe that it looked like a bacteria on Earth. And then they claim that this is evidence for ancient Martian life. So of course, it's an interesting idea. And actually the president of the United States, Bill Clinton at the time, actually made a speech about this big discovery. But then a few years later, a group of scientists found that you can actually use purely inorganic processes to get structures that are kind of like this. So this is really not hard evidence for life. So what is the lesson we can learn here? One thing is, of course, you cannot judge by the look to say anything is bio or not bio, right? But then there is also another interesting lesson we can learn, that is using purely inorganic processes, you could also get complex ordered morphology. So how do we characterize that? How do we write a theory to characterize the assembly of complex ordered morphology from simple inorganic building blocks? Okay, so to make this question a little more concrete, let's look at some more examples. So these are images taken from a paper published by my colleague Nick Kotoff at Chemical Engineering at U of M. In this experiment, they took gold thiolate nanoplatelets, which are small nanoparticles that are plate-like, and they are curved because they are coated with surface ligands that are these chiral molecules. And then they let these nanoplatelets assemble in solution. They find very interesting complex morphologies, like in these images, that if you just look at the picture, you might also think it's coming from biology, but it's assembled in a lab. So I realized that this is perhaps a very interdisciplinary audience. So let me explain a little bit what are the basic concepts here. So what are nanoparticles? Nanoparticles are just defined as particles of matter of size of about 10 nanometers, right? They can have chemical composition of all kinds of different atoms and the molecules. So basically the structure is often that you have a core of a group of atoms. It's sometimes crystalline, sometimes amorphous. And then they are coated with some surface surfactant or polymer or something more complicated. And then at different conditions, they can assemble into interesting structures. And this process has a lot of applications for various properties, because these nanoparticles have, for example, a very large surface area to volume ratio, so they can be used for many applications, and they also carry interesting quantum states and have interesting optical properties. So the concept of self-assembly really just refers to the autonomous assembly of some target structure by designing the building blocks. So you design some building blocks where then by either thermal fluctuations or out of equilibrium fluctuations, the building blocks can find each other and assemble into something you want. So these are the sort of the basic concepts we're going to use in this. So this is one example. And here is another example from the same group, where they take semiconductor nanoparticles. Here, the particles have the shape of tetrahedra, and again, coat them with surface ligands and let them self-assemble. And they find, again, a number of really interesting complex morphology, from helices to bundles and bow tie-like structures. So the interesting physics question I see from these experiments is really how does the system start from some very simple building blocks, in this case, just a simple regular polyhedra, and gave you these complex and yet ordered structures. How did this happen? So if we think very generally about complexity, we can see that in physics, complexity can come from different sources. For example, nonlinearity and out of equilibrium processes. And here, in what we are going to talk about today, we are trying to argue that there is an interesting new source of complexity that comes from non-Euclidean geometry. So how does that work? So if you think about the building blocks in these experiments, one thing in common between them is that there is a geometric frustration because the building blocks won't fit nicely together. So in the first experiment, the nanoplatelets are twisted because of the surface ligands. And this twisting prevented them from stacking perfectly to one another. So they split when they try to bundle, and then this splitting gave rise to interesting structural hierarchy. So this is a geometric effect that gave the complexity you see. And in the other experiment, similarly, there is also a geometric frustration. So if you take a perfect tetrahedron and try to pack them together, it's well known in geometry that they cannot tile 3D space. So if you take 5 tetrahedra and bundle them and put them together around an edge, the dihedral angle is such that 5 times the dihedral angle is almost 2 pi, but there is a deficit that gives you this small gap. And if you take a 20 tetrahedra, again, you can almost make an icosahedra, but again, leaving little gaps. So this is the geometric frustration. So what is the effect of geometric frustration when you take these building blocks and try to assemble them together? Right? It's like trying to assemble something that cannot be assembled. So we know that when people usually do self-assembly experiments, they try to design the building blocks so that they nicely fit together, and then you can get large, beautiful crystals like in this picture. However, when you make the building blocks in a way that they are geometrically frustrated, most of the time, you're going to get something not very interesting. You just get some disordered open network that's amorphous, and you cannot control what you get. So that's not super interesting, right? However, in these recent examples, in these recent experiments, you see that if you're able to control the pathway of the self-assembly, it is actually possible to make use of this geometric frustration and get morphology that is complicated and not reachable from perfectly fitting together building blocks. So you cannot get these assemblies from building blocks that perfectly fit together. It needs the geometric frustration to happen. Okay, and just to add a little bit, in these self-assembly experiments, there are a number of interesting ways you can control the morphology. You can control the interactions between the nanoparticles and use the computation between attraction and repulsion. You can also control the reaction kinetics. Here, to give you an order of magnitude, the binding energy between the nanoparticles is many times kBt. So this is a quite out of equilibrium process. Okay, and then you can also change the geometry and the chirality of the particles and use that to influence the self-assembly. Okay, so this generally belongs to the general problem of geometrically frustrated self-assembly. So this is a field that has been studied a lot in the past decade, and there are a number of interesting effects that people studied. So for example, if you try to assemble spheres on a surface, it is known that if you have a flat surface, you can pack them perfectly, right? You just have a hexagonal order. And if you introduce curvature into the surface and then try to pack disks or spheres on this surface, there is a geometric frustration and you get topological defects. So that's one interesting example of geometric frustration. And another example is when you try to take a bunch of fibers and bundle them together, but the fibers are chiral so that they have a turning between one another. And this also introduces a geometric frustration. And if you write down the theory, you will see that it's actually the same mode of geometric frustration between this case and this case, because there is a positive Gaussian curvature. And then here is another interesting study where people try to study the case of introducing geometric frustration in the packing of hexagons. So you know that if you have a bunch of hexagon tiles, you can tile your plane perfectly. You can tile your floor perfectly, right? But if these hexagons, for some reason, deviate from the perfect shape, if 3 edges are longer than the other 3 edges, then the packing is frustrated. And depending on how you tune the computation between the attraction and the geometric frustration, you can get different shapes like a tree-like structure or fiber or bulk assembly. So this tells us that there is a lot of interesting problem when you try to add a little bit of frustration to the system you study. And if you're interested, this is a nice review that recently published about geometrically frustrated assemblies. So a lot has been learned in this field. And in particular, we know that if there is geometric frustration, the assembled structure is typically pre-stressed. So even if you don't give any load, the structure itself is stressed because of the geometric frustration. And they also have self-limited growth, because if you consider the free energy as a function of the size of the cluster, there are competing terms from the frustration and the surface energy. And when you add them up, there is often optimal size. And this also generates topological defects. So there's a lot of interesting questions. And the new question we are trying to study in our research here is the following. Can we develop an analytic theory to program the morphology of frustrated self-assembly and then control the complexity of the assembly? So that's a sort of a new direction we are trying to go into in this study. So this leads us to the work I would like to mainly discuss today, this preprint on frustrated self-assembly of non-Euclidean crystals of tetrahedral nanoparticles. So this is done in collaboration with my postdoc, Francesco Serafin, and Jun Lu, who is a postdoc working with Nick Kotoff. They are at chemical engineering here, and also Kai Sang, who is in our department. I think many of you know him. So here we are going to start from this experiment and write a general theory for the geometrically frustrated self-assembly of polyhedral nanoparticles, and use that to see if we can program complex morphology from tuning this geometric frustration. And we will talk about the interesting relation to other problems and ongoing work. And I'd like to also take the opportunity to acknowledge fruitful discussions and also ongoing work with Sharon Glotzer and her postdoc Philip and student Ye, and also my student Nan. Okay, so let's now look in a little more detail in this experiment. So here, like I mentioned, we have these tetrahedral nanoparticles, and they are coated with surface ligands. And these surface ligands induce face-to-face binding between these particles. And there is also electrostatic repulsion between the particles. So this tells us that they will first assemble into one-dimensional structures, which is this so-called tetrahelix. And the assembly of tetrahedra into tetrahelix is not frustrated because you can reach perfect assembly of 100% volume fraction, and there is no geometric frustration. The geometric frustration happens when you try to bundle these tetrahelices together. And because the effect that the dihedral angle don't fit together to give you 2 pi, it's frustrated and you have these little gaps. So I have some 3D printed tetrahelices, and if we are doing this talk in person, I'm going to pass it around, but anyway, I'll just show you here. If you try to bundle them together, they split because the geometry don't fit together. This is really what I refer to by geometric frustration, okay? And interestingly, if you introduce curvature into your space, you can close these gaps and then make it pack into a perfect crystal. So basically, if you introduce positive Gaussian curvature, you can close the gap, and the curvature also induces a bending of the main axis of these tetrahelices, and then they bind into a ring. And so this tells us that you can get a perfect crystal of tetrahedra in curved space, although they cannot give us a crystal in our space. Okay, so how does this work? It's quite abstract to think about, right? So let's use a simple two-dimensional example. So if you have a bunch of tiles that have the shape of pentagon, and try to use that to tile your floor, you know that it doesn't work, right? Because the internal angle don't add up to 2 pi, and you get gaps. But if you make your floor curved, they can tile your floor, right? It's not something you want to do to your actual floor, but as you can see in the example here, if you introduce curvature, you can close the gap, and they actually make a dodecahedron. And in this case, all of the nodes live on a two-sphere, which is the surface of a sphere in 3 dimensions. Okay, so this is how introducing curvature can get rid of geometric frustration. So I have a simple video that I took from YouTube that can show you this effect. So if you introduce curvature, you can close it up. So that's pretty obvious to see. Okay. So it's pretty similar to use this kind of concept to think about self-assembly in 3 dimensions. So here, let's take the example of dodecahedron and try to pack them together in flat 3D. So in flat 3D, if you calculate the dihedral angle, you will see that there are little gaps. They cannot pack together. Even if you close the gaps by changing the shape a little bit, we know that it still doesn't work because this type of icosahedral order cannot propagate in 3D space. It's not a subgroup of rotation in 3D space. Okay, so again, if you introduce positive Gaussian curvature, you can make them assemble into a perfect crystal. So let's look at this video to see how that works. So if you take a bunch of dodecahedron, you can make them pack into 1D chain. That's a perfect step. But then when you try to bundle these 1D chains together, you get gaps that is intrinsic to our space, right? However, if you take 2 such bundles and put them next to each other and introduce positive Gaussian curvature, that's what's happening in this step. When you introduce curvature, you can make them perfectly pack a curved 3D space with no gaps. And what you get is a perfect crystal. It's a so-called 120 cell. It's a regular polytope. Polytope is an extension of polyhedra to 4 dimensions. Okay, and here, analogous to the 2D case, all of the nodes live on the 3-sphere. So the 3-sphere is the surface of a sphere in 4 dimensions. It's analogous to the concept of 2-sphere, which is the surface of a sphere in 3 dimensions. Okay, so here in this picture, it again looks distorted, but in the actual crystal, all of the dodecahedron are the same to one another. They look distorted here is because we're projecting from 4 dimensions to 3 dimensions. Okay. So the packing of tetrahedron is very similar. I don't have a video for that, but the packing of tetrahedron is also that when you introduce positive Gaussian curvature, you can close the gap and get a perfect crystal. That's a so-called 600 cell. Again, here, all of the nodes live on the surface of a 3-sphere. And in fact, the 600 cell and the 120 cell are dual polytopes. They are dual into one another by the mapping of node to cell and etc. Right? It's in the sense of dual polyhedra. Okay, so these are nice mathematical concepts that has been known for a long time. So why is it relevant for physics? We believe they are relevant because they represent true ground states of the packing problem of these polyhedra. So like we mentioned, if you think about a tetrahedra, their packing is frustrated in 3D Euclidean space, in the space we live in. So we cannot get a perfect crystal where everything packed with 100% volume fraction. However, in a curved space, you can have a perfect crystal, and it represents a true ground state because you have a 100% volume fraction. Obviously, that's the lowest potential energy packing if these particles are attractive or have attractive interaction to one another. That's the lowest potential energy state, right? So they represent a true thermodynamic ground state, although this ground state doesn't live in the space we live in. So then this gave us ideas to think about what is the indication of this curved ground state for physical problems in our space, right? So to just give you a little bit of evidence of why this is actually a relevant ground state, let's look at some old Monte Carlo simulation. So in this paper, the author studied Monte Carlo simulation of sphere packing in curved space. So sphere packing and tetrahedral packing are actually due to one another because you can put a sphere at the tip of the tetrahedron. You can put spheres at all of the tips of the tetrahedron, and then you can see that there is a duality between sphere packing and the tetrahedral packing. So if you arrange a sphere on the 120 cell, they are perfectly touching one another. So the 120 cell represent an unfrustrated packing of spheres on the 3 sphere, right? So sphere packing in our Euclidean 3D space is frustrated. So then if you run Monte Carlo simulation of sphere packing on a 3 sphere, you can see that the Monte Carlo simulation very quickly converges to the 120 cell, which is the true ground state of the problem. And on another hand, if you run the Monte Carlo simulation in Euclidean 3D space, eventually you get the FCC lattice, which we know is the closest packing you can reach in our Euclidean 3D space. But you need many, many Monte Carlo steps. And the reason is really that this FCC packing is a frustrated packing of spheres in Euclidean 3D space, and in contrast to the happy packing of 120 cell on the 3 sphere. Okay, so this Monte Carlo simulation tells us that these ground states, if you have the right curvature, is actually pretty easy to reach. But we don't have such a curvature in our space, right? So in some sense here in this study, they are looking at completely different crystal structures, the 120 cell in curved space and FCC lattice in our space, and they have different assembly kinetics. And the interesting new question we try to answer here is, what if we try to bring this crystal to our space? If we try to have the crystalline order from the non-Euclidean space and to try to push it to our space, what are we going to get, right? So the theory that we presented in this paper is trying to provide a recipe to do this. So basically, we start from non-Euclidean crystals, which provide true ground states. And then these ground states cannot be realized in our space. However, we take them as ideal reference metric to write a continuum theory to describe the self-assembly in our Euclidean space. And that can guide us to find the stressed morphology of the assembled structures. Okay, so next I'm going to just sketch a little bit of the steps of how to do this theory. I don't want to go into too much detail here. So firstly, we need to understand the internal structure of these non-Euclidean crystals. They are a lot more complicated than Euclidean crystals. So firstly, like we said, if you try to bundle together these tetrahelices, they cannot fit in our space. But you can take 5 of them and introduce a little bit of Gaussian curvature, they can close and give you a ring of 5 tetrahelices, okay? And then you can attach outside of this ring another 5 tetrahelices and get something like this. And then you can wrap that with another 5 tetrahelices and get this thick bundle. And then outside of that, you can take another group of 5 tetrahelices and stick it through this hole and close the whole thing. That gives you the so-called 600 cell structure. It contains 600 tetrahedra, which are grouped into 20 tetrahelices. So here you can see 5, 5, 5, 5. And they form 4 interlocking toroidal shells. And each of the tetrahelix is 30 tetrahedra long. So it's a complicated structure, and you can understand that using a discrete Hopf fibration. You start from base icosahedron, where each of the triangle represent a tetrahelix, and then they are linked to one another by a link number 1. Okay, so that's basically the internal structure. And then the next step is to find a coordinate system to label all of the building blocks and then calculate the metric. So here we find a coordinate system where you can use the first coordinate to go from one shell to the next shell, and then the other two coordinate labels the building blocks within each of the shell. In particular, beta and theta are along the left-handed and right-handed tetrahelices, respectively. Okay, and then using this coordinate system, you can calculate the metric, which tell you what is the ideal distance between these building blocks they want to be, but they cannot realize that in 3D space. Right? So you can calculate the metric tensor and test that the Ricci tensor, which is from the curvature of this metric tensor, and you see that there is a constant positive Gaussian curvature that verifies that you cannot realize it in 3D space. Okay, so now we have a mathematical formulation to understand this crystal. The next step that is really the important physics is to cut a piece of this non-Euclidean crystal and try to see what kind of shape it takes in our Euclidean space. The reason we want to cut is that if you try to take the whole 600 cell to our space, it's going to be highly frustrated. There is a lot of stress because you're trying to fit together something that cannot fit, right? So the more, the lower energy configuration is really to have a thin sheet or a bundle from it. So another reason is that these particles are charged. So the electrostatic charge will prevent them to grow from growing large 3D clusters. So you will get thin structures. So here, as a first step, we choose to take the two middle toroidal shells and study what is the morphology of this sheet. Okay, and in particular, the criterion for choosing this particular subsection of the non-Euclidean crystal is twofold. Firstly, this is a sheet with smooth surface, so we have low surface energy. And secondly, the metric is not dependent in the surface. So that you get homogeneous metric in the surface. The metric only depends on the thickness direction. Okay, so then we can use this to calculate the morphology. So I'm not going into the detail of the math here. So basically, you have an energy that has 4 parts. The elastic energy that takes care of this geometric frustration of fitting something together that cannot fit. And then there is the electrostatic repulsion. And we also have binding energy and boundary energy. But these 2 terms will not change after you make this cut. So it is really the first 2 terms that determines the morphology. So we can write the elastic energy using a thin shell expansion and make the problem more tractable. So it contains a stretching elastic energy and a bending elastic energy. And then we can use the same type of thin shell expansion to write the contribution from the electrostatic repulsion. And when you add that to the elastic energy, you will see that the repulsion both stiffens the sheet and also flattens it. It changes the curvature of what it wants to be. And then putting it all together, we can minimize the total energy and find the morphology. So eventually we find that there are 2 regimes. In one regime, when the ribbon is narrow, the morphology is a helicoid, and we can calculate the embedding of this helicoid in our space. And when the ribbon is wider, you will get a cylindrical helical ribbon. But the experiment we're interested in is mainly in the narrow regime. And this narrow regime is determined by the repulsion, actually. So it may be somewhat counterintuitive to think about how tetrahedron makes helicoids. Right? So here I included some images from an ongoing computational work in collaboration with Sharon Glotzer's group, where we take these structures from the 600 cell and run the simulation in flat space and see what shape they take. And then you can see here, indeed, the tetrahedra can make these helical structures that look similar to the experiments. Okay. So, okay, then we can take the result and compare with experiments. So in the experiment, you can change the chemical parameters and use that to tune the electrostatic repulsion. And when you tune that, you change the pitch of the helicoids, and we can compare the predicted pitch with the experimentally measured pitch, and we see good qualitative agreement. So this shows that we can actually have a tuning knob to change the morphology of the assembled structures. And this provides us with some control with this for this complicated self-assembly problem. Okay, so that's basically how our theory works. And in the rest of the time, I would like to just chat a little bit beyond this and think about other related theoretical problems. One interesting problem is about chirality, right? So in the experiment, you see that you get a pretty pure either left-handed or right-handed helices. So where is this chiral symmetry breaking from? We know that in the beginning, the ligands you attach on the tetrahedral particles are chiral. So, and in fact, indeed, that if you start from left-handed ligands, you get these left-handed helices. And if you start from right-handed, you get right-handed. However, it's actually quite non-trivial to think about. So these ligands are molecules that are about a nanometer size. And the structures, the chiral structures in the end you get is 1,000 times larger than this. How did the chirality at such a small scale propagate up the length scale to give you quite a pure chiral assembled structures? So this is not obvious indeed. So if you look into the literature, you will see that chiral symmetry breaking is actually a very intriguing theoretical problem. So here in this interesting review on reviews of modern physics, the authors talked about chiral symmetry in these molecular and larger scale problems. And as you can see from this figure, if you take a molecular scale chiral objects and try to assemble them together, depending on the interaction and the pitch, you can either start from right-handed and get right-handed at the larger scale, or get left-handed at the larger scale. It's not obvious how it works, right? So in our problem, in fact, the 600 cell, the non-Euclidean crystal we start with is not chiral. And also the sheet we cut is not chiral. The mathematical step that broke the chiral symmetry in our problem is really when you cut a long ribbon, which direction do you choose for its long axis to be aligned with? So that's the mathematical step, but what is the physical reasoning of in the experiment? How does the system choose which direction I want to grow longer? So our hypothesis is that this is a kinetic problem where the chiral molecules determine how the nanoparticles bind together. So when you have left-handed molecules, when the particles bind, there is a small twisting between the particle and its neighbor. And of course, also right-handed, it will twist in the other way. And this actually energetically select which type of tetrahelices they will grow into in the early stage of the assembly. And as you can see, if you have right-handed ligands, the right-handed tetrahelices will be of lower energy. And then in the next stage of the assembly, the resulting ribbon will be more likely along the right-handed direction. And this is what we hypothesize to be the pathway of chirality propagation from small scale to larger scale. And I just want to mention that in the literature, there are a number of interesting studies of what do we actually mean by chiral symmetry breaking. So chiral symmetry is really the symmetry of something looks the same with its mirror image. And it's a quite an elusive concept. And in this experiment, the authors show that you can take the same system and cut it in different directions and let the system adopt its lowest energy configuration. And depending on how you cut, you get different chiral structures. And similarly, there are also these topological defects in liquid crystals where you go along different directions, you get a different handedness. So this handedness and the chirality is a very interesting question to think about in self-assembly problem. And here, the structure is very similar to the 600 cell, internal structure that we talked about. So that's one thing. And at last, I would like to just sort of generalize this problem to other types of polyhedra. So far, we just talked about tetrahedra, and we said that its assembly is geometrically frustrated. But in fact, if you think about other types of polyhedra, so we know that there are 5 different types of regular polyhedra in our 3D space. Here I'm listing the 5 of them. If you think about the assembly, the packing problem of these 5 regular polyhedra, you will see that geometrical frustration is really the rule rather than the exception. Among them, only the cube can happily tile flat 3D space. All of the others have dihedral angles that cannot pack in 3D space. So either you need a positive Gaussian curvature and go to a 3-sphere, or you need a negative Gaussian curvature and you go to hyperbolic 3 space. And you can get different types of crystals from them. And the reason that one polyhedra can tile into different crystals is really how you pack them. So let's again take tetrahedra as one example. So these polytope or the non-Euclidean crystal can always be labeled using this so-called Schlafly symbol, where P and Q represent the number of edges around each face and the number of faces around each vertex. So these are already fixed when you choose the polyhedra. And then the last parameter is how many polyhedra you fit around each edge. Here you can fit 3 of them together and close, and you get the so-called 5-cell, which is a polytope. And you can also have 4 of them and force it to close and get the 16-cell, or 5 of them and get a 600-cell. And you can even have 6 of them, which overlaps, but you can introduce a negative Gaussian curvature to get a non-Euclidean crystal. Okay, so here, this one is least frustrated because as you can see, it's very close to 2 pi. You only need a little bit of positive Gaussian curvature. That's why we chose this one to study our problem. All of the others need a lot more curvature in order to close the gap and fit into a perfect crystal. So then from this, you can see that our theory provides a general framework to study the self-assembly. You can always follow this recipe of first setting a packing rule, and then get the non-Euclidean crystals and find the metric and cut a domain and calculate the morphology. So this seems to be a sort of a straightforward thing. So in the beginning of the talk, I mentioned the complexity. So how do you get complexity from this? So complexity can emerge at different steps. One important step that will give you complexity is really how you cut a domain, right? There are a number of factors you need to consider of which part you cut from a non-Euclidean crystal. You need to consider interactions, frustration, and the kinetic pathway. And our conjecture is really that you can use this to program complexity in this new non-Euclidean design space. And by choosing the different types of domains you can cut, you can reach a number of very interesting morphologies, from ribbons and sheets to more complicated boundaries and hierarchy. So here, by control the surface energy, you can really control the natural tendency for the structure to split because of the geometric frustration, and reach a number of interesting morphology that look like biology. Okay, so now coming back to the initial question we posed at the beginning, right? So how do we reach this Goldilocks zone and realize interesting functions and robustness in the structures that we engineer, right? So if you think about the pathways to go from order to disorder, there are many different ways you can go. You can use topological defects. You can use repeated healing and cooling to turn a crystal into an amorphous structure. And here we're taking a particular path of non-Euclidean geometry. The reason we are taking this path is that it's particularly mathematically tractable to introduce some geometric frustration, and that makes the geometry into a non-Euclidean problem. And then it's a solvable mathematical problem. And then the one sort of a take-home message is that if, for example, if you have a nice experiment where in the system you study, there is some happy self-assembly problem. You can think about introducing a little bit of geometric frustration into the problem, and the result you get might be an interesting surprise. Okay, so in the end, I would like to just comment on why do we even want complexity? What do we gain by making things more complicated? Right? So there are many benefits. So for example, if you can generate a structural hierarchy, you can gain a number of nice properties, such as lightweight, strong material, and a greater design space for complex functions. In this example, you see that by introducing a structural hierarchy, you can tune the band structure of some metamaterials, and it also makes things more reconfigurable. And one sort of philosophical question to think about is, why do we even like crystalline structures to start with? One obvious reason is that they are equilibrium bulk phases of atoms that we always see, and they are also easy to describe mathematically. But we need to understand that crystalline structures is only a very limited subset of structures that you will see in nature. By broadening the horizon and look at structures that are more complicated and yet ordered, you can maybe gain a lot of interesting new properties. And another interesting practical route is that the structures you get from this type of frustrated self-assembly is always strained or stressed, in another way to say it. And controlling the strain can take interesting effects on a lot of properties, such as electron properties and vibrational modes or magnetic properties. And here we sort of get strain engineering for free from the non-Euclidean geometry. So we expect to realize a number of interesting new features from these materials. Okay, so to end the talk, we studied the interplay between self-assembly and the non-Euclidean crystals, and we propose that this is a fruitful route for us to get a controllable complex morphology and novel functions. So thank you for your attention, and I would like to welcome questions. Okay, I will for now stop sharing.
Thank you so much. I really love your talks. It was a really cool one. I guess I have a question if no one else has one. I'm kind of curious how much, so the methods to get from the like ordered to, no, not ordered to disordered, like the more complex structures, with the exception of non-Euclidean space, were those methods inspired by biological processes that like we see in nature to arrange particles, or is it unique to inorganic compounds, and then like other possibilities that we can try that we observe from biology?
Yeah, I think it's sort of twofold. So we're inspired by biology to think about where are these complicated structures from, but the method is very general, right? You can use it for different types of systems. So whenever you have a self-assembly problem where the building blocks are geometrically frustrated, you can always ask the question, can I introduce some curvature to make them perfectly bind? And then you can write a theory in that curved space first, and then you try to bring it back to our space and see what happens. Right? That's sort of the big picture.
I guess I also have a quick question. I know you talked about how you can describe the strain mathematically that you get from curving these structures, and then you said later that the strain can, create different properties in 3D materials. Is there a way that you can easily map the two to each other, or is it kind of two different ideas? Like, can you, if you were to take your complex materials, can you kind of understand what kind of properties they may have?
Yeah, so are you referring, so I think I introduced a strain because the structure cannot realize this ideal metric, right? So there is always a strain. And what is the second strain you're talking about?
What you mentioned in your second to last slide, I believe.
Oh, okay. So let me show that here. Like here, right?
Yes.
On the strain engineering.
Mm-hmm.
Yeah. So here, I think I'm including some example where people take initially not a strained material like graphene, right? So flat graphene is not frustrated. You just have a nice sheet, and then people try to make it strained by putting it on a non-flat substrate or doing some tricks to introduce a strain, and then this strain will affect the electron wave function, right? So the point I'm trying to make here is that if you try to, for example, write this electron Hamiltonian for the non-Euclidean, for the assembled structures that has an intrinsic non-Euclidean metric, you always have a strain to start with, right? You cannot get rid of the strain. And that strain is sort of coming for free, and you don't need to do complex tricks to introduce the strain. So it is the same type of strain, if that's what you're asking.
Yeah, that's it. Okay, great. Thank you so much.
Okay, yeah.
If you think of other questions later, I CC'd Professor Mao on the announcement email, so you can always send her an email if you think of a question after. I'll stop the recording for now, I guess.